Okay, good day, grade 11s, and welcome to a session on acids and bases. Okay, session falls under chemistry, as you all know it, and it should be covered in your term 3 syllabus, I'm assuming. But anyway, okay, so in this topic, we will be looking at different types of acids, different types of bases, what defines an acid, what defines a base, the two theories that define an acid, the two theories that define a base, and we're going to talk about words, things that we call ampholyte. We're going to talk about acid proticity. We're going to talk about conjugate acid base pairs, the pH scale, weak acids, strong acids, etc. But in this particular video, we are going to look at mainly the introduction of acids and bases, that is, defining what an acid is, defining what a base is, according to the Arrhenius theory and what we would call the Laurie-Bronsted theory, talk about acid proticity, and then in a different video, we're going to look at conjugate acid base pairs, ampholytes, weak acids, concentration acids, and so on. Okay. For starters, we look at the Arrhenius theory. So back in the 1800s, well, I'm assuming it was in the, if I'm not mistaken, 1885 or 6 or 7, just between those 2 years, there's a guy named Arrhenius. I don't quite know his name, but so Arrhenius was a guy, and he came up with a certain idea, right, behind defining what an acid is, defining what a base is, right? So Arrhenius woke up one time and was like, okay, did a few experiments. Then Arrhenius came to this particular conclusion. Arrhenius said, an acid by definition is a substance, right, so an acid by definition is a substance that actually produces hydronium ions. It produces hydronium ions or hydrogen ions when what happens? When it is dissolved in water. So you dissolve a substance in water and it gives you hydronium ions or hydrogen ions, which by the way are soluble. I mean, in essence, every ion is soluble. So a substance that produces hydronium ions and H plus ions is dissolved in water, right? And we say that a base, by definition of the Arrhenius theory, a base is a substance, right, that produces what? Hydronium. Sorry, so sorry. I got a little bit carried away there. Produces hydroxide ions. Supposed to be OH minus, just for those who don't see. That's OH minus. It produces hydroxide ions. When what actually happens? When you dissolve it in water. Right? So in this particular case, we look at the first definition and it talks about H3O plus, and it also looks at H plus. What is what and which is which? In essence, H3O plus is no different from H plus, right? With the condition that when you work with what we call protons, you do not make a mistake and you mistaken a proton and you say that a proton is an H3O plus ion. No. When we talk about protons, we say that protons, by definitions, are H pluses, right? I mean, from grade 10s, you know that protons are positively charged particles, right? So particles that are positively charged. So in this particular case, a hydrogen ion in acids and bases, we say that it is a proton. So when we talk about a proton, we talk about a hydrogen ion, right? Yeah. Coolios. And then there were two other guys as time went on. Now, this was in the 1920s, I'm assuming. In the 1920s, we had two guys, Laurie and Bronsted, and they came out with the same idea of an acid and base. It's quite different from the Arrhenius definitions, but in essence, it all boils down to the same thing. Right? So we talk about an acid in terms of the Arrhenius theory. We say that a substance is defined to be an acid if and only if it produces hydronium ions in water, right? we say a substance is considered to be a base if and only if it produces hydroxide ions when dissolved in water. So, by definition of the Lowry-Bronsted theory, which is very short as you can see, an acid is regarded as a substance that donates a proton, or rather a proton donor, right? Something that donates H plus is what we call an acid, right? And obviously, if something donates something in an acid-base reaction, if something donates something, then something must collect or receive that something. Okay, and I just realized that I've said an awful amount of some things, But anyway, so as I donate a proton, I'm an acid. I donate a proton as a base. I am required to accept or receive that proton. So it's a proton acceptor, or some can say a proton receiver, right? So it accepts protons or it receives a proton. Coolios. Now, so we've spoken about an acid under the Arrhenius theory, a base under the Arrhenius theory. We've looked at the Lowry-Bronsted theory acid, the Lowry-Bronsted theory base. And we've spoken about protons. We said that a proton is an H plus and not an H3O plus. Please don't make that mistake. And we've basically just said, like I said, acid and base definitions in terms of the Lowry-Bronsted theory and the Arrhenius theory. Definitions are different, but it all boils down to the same thing, right? So for starters, say we had just a typical example. So in this example, we have hydrochloric acid that just reacts with water. And what does that actually give me? That gives me, now if I just move on, right? Remember that HCl, wink, wink, nudge, nudge, is a strong acid, right? Meaning it it ionizes. Just a reminder, NB. Acids ionize and bases dissociate. Just an NB for you right there. So we say that acids ionize and bases dissociate, right? Right, so an acid, HCl, is a strong acid and it ionizes completely to form H plus and Cl minus ions, right? So what basically happens? So these H plus ions, well then, remember it is an acid, according to the Arrhenius, the Lowry-Bronsted theory. An acid is a proton donor. It's a proton, an H plus donor. What do you know? When something donates something, it gives away something, right? So I then say that H plus being a proton donor, HCl being a proton donor, is going to give away its H plus. Where does it give it to? To the water, right? So what you have then is an end result. Remember, now in HCl you have H plus and Cl minus, but then you gave away H plus. That means you only have Cl minus left plus H, notice 3O plus. Now, where does the 3 come from? Now, remember, in H2O, we have 2 hydrogen atoms, and then we add another one. That makes us H3. But we didn't just add, remember, we didn't just add an H, but we added an H plus. So this makes us have H2O, just realize this is H3, along with its charge, right? Hence we result in H3O plus, right? Okay. Now, so we have that. Now, the reason I would basically let me just move this down, just to bring it down a bit. Okay, there we go. Now, the reason I would basically say that the Arrhenius theory and the Lowry-Bronsted theory, though different, somehow mean the same thing, or somehow boil down to the same idea, is this. Notice something. According to the Lowry-Bronsted theory, I notice that this guy right here HCl is a Lowry-Bronsted, just gonna write LB acid, right? It's a Lowry-Bronsted acid. Why? Because by definition, a Lowry-Bronsted acid donates an H plus. So that is exactly what HCl did. It gave away an H plus, and then we are safe to say that the H2O is a Lowry-Bronsted base. Why? Because when the HCl gave away the acid, the water accepted, not the acid, I'm so sorry, gave away the proton, the water accepted those protons, right? By definition, a base is a proton acceptor, by definition of the Lowry-Bronsted theory. And then, when we go back to the Arrhenius theory, we then are told that it is a substance that produces an acid. By the Arrhenius theory, is a substance that produces hydronium ions, right? So if you go back here, notice something. We have indeed produced hydronium ions, right? We have produced a hydronium ion. Therefore, we are safe to say that HCl is an Arrhenius acid. Why? Because it produced a hydronium ion, and it is also a Lowry-Bronsted acid. Why? Because it donated a proton. Right. Now we look at a different example. So that's basically how an acid would work rather. Now we look at a different example, and we look at how a base technically works. So if for a different example, and we talk about a base, let's take ammonia, right? Ammonia is a base, and it reacts with water, a weak base, by the way. And what basically happens is this. So ammonia being the base, right, which is, by the way, a weak one, remember that bases dissociate. So what happens with ammonia is that ammonia does not fully dissociate, right? So it is not expected for ammonia to form like one would expect N3 minus plus 3H plus, right? Because it is a weak base. What actually happens is that NH3, remember, it is a base. What is a base by definition of the Lowry-Bronsted theory? A proton acceptor. So H2O will give away proton, right, to NH3. So what does it become? It becomes NH. Remember, we had 3 in ammonia. Now we have NH4, but we didn't just give away a proton. Sorry, we didn't just give away a pure hydrogen. We gave away a hydrogen ion. So we have its ionic charge plus OH minus, right? So we have ammonia reacting with water. Water becomes the base in this case. So we can say that the water then becomes the Lowry-Bronsted base, not the base, but the acid, the Lowry-Bronsted acid. Why? Because it gave away its proton, and then the ammonia can then be the Lowry-Bronsted base, right? Then what is then forming? So we notice now we've spoken about the Lowry-Bronsted acid and the base. We've defined a base in terms of the Lowry-Bronsted theory. And when you look at the definition of the Arrhenius theory, we said that a base is a substance that produces OH minus ions, right? So that means if you look at this, what did we produce? OH minus ions, right? So we've produced an OH minus ion. So this already qualifies ammonia to be an Arrhenius. Yes, you got it right. An Arrhenius base, right? Why? Because it produced OH minus ions. NH3 is also a Lowry-Bronsted acid. Why? Because, sorry, a Lowry-Bronsted base. Why? Because it gained a proton. Okay. And then, right. So, just an NB for yourself. Just don't remember. Just don't forget. In essence, the number of hydrogen atoms in a compound, be it in an acid, to be precise, the number of hydrogen atoms in an acid, a pure acid like HCl, the number of hydrogen atoms, will actually tell you how many, it actually can tell you how many protons can be given away. Remember, an acid gives away protons. How many H plus? How many protons can be given away, right? So what tells you about that? The number of hydrogen atoms, right? So that's when you introduce something called acid proticity. Okay, so look at acid proticity. So what is acid proticity? So we're looking at acid proticity. So with a typical example of HCl, right, you then notice something. HCl only has one hydrogen atom, meaning it can only donate one proton, right? And we call something that can only donate a single proton a monoprotic substance. We call it a monoprotic substance, or rather acid. It's better if we can just say a monoprotic acid, right? So something that can donate a single proton is known to be monoprotic. Remember from grade 10, sorry, from mathematics rather, mono means one, right? So mono means one. Okay. So we've noticed that HCl only has one hydrogen atom, meaning it can only lose one proton, right? And as we look further, we notice that, take a different example. Take H2SO4. What can this give me? Judging by, notice something, judging by the number of hydrogen atoms, I know that I can lose at most 2 protons. I can donate at most 2 protons. That's what the number of hydrogen atoms actually tell me, that I can donate 2 protons, right? Now let's see what actually happens. Right, so I have H2SO4, and what do we call something that can donate 2 protons? Something that can donate 2 protons, we refer to that as a diprotic acid. We say that it is a diprotic acid. Remember, for math, once again, di means 2. Okay. But how does this actually happen? Remember, sulfuric acid, or hydrogen sulfate, is a very strong acid. It has a P. Okay, and just relax. It has the value of the pH is quite close to 0, right? Way far from 7, just below 7 and very close to 0. So it's a very strong acid. And we would know with time that a strong acid ionizes completely. Remember, acids ionize, bases dissociate. So a strong acid basically ionizes completely. So which means that with H2SO4, I am expecting H2SO4 to lose how many protons? 2 protons, right? So what we will actually do is to write down the reaction. So we're going to write down the ionization of H2SO4 one hydrogen at a time, meaning we're going to start by losing one hydrogen and then lose the second hydrogen, right? So when I lose one hydrogen, notice I am then going to be left with HSO4 minus. Now, I had 2 hydrogens, I lost one, now I only have 1. Where is the other one? It becomes H plus. So I lost an H plus ion. I lost a proton. Yes, I lost a proton. This is a proton. Great, so I lost a proton. But then you notice something else. This negative sign here, remember there's a 1 right there, just an invisible 1. But that basically just tells me, besides the fact that it's a charge, In essence, you could think of it this way. It basically tells me how many protons have I lost thus far. With reference to the initial guy right there, how many protons have I lost thus far compared to the original guy, H2SO4. Now, that -1 tells me I've lost 1 proton thus far. Which one is it? That guy right there, right? And I noticed something. The HSO4 minus can lose another H because it has another H to it. So it can react once again, and it can be HSO4 minus to give me SO4 2 minus plus NH plus. Okay, so that's what I have. So I have SO4 2 minus plus NH plus. Now notice something. I had 1 hydrogen here. Now I have nothing. But then I also have my charge of 2 minus. So what does that charge tell me? It tells me that I have lost 2 protons with respect to the original guy right there, right? So this original guy so far breaks down, ionizes and forms SO4 2 minus, meaning it lost 2 electrons. Sorry, man. So sorry. 2 protons, right? So it loses 2 protons and forms SO4 2 minus. So where are the 2 protons that I've lost? This guy right here plus this guy right here. These two give me 2H plus. Those are the 2 protons that I have actually lost, right, from the original H2SO4. Remember, the number of hydrogen atoms tells me how many protons I can donate, and because I had 2 hydrogen atoms in sulfuric acid, that means I can donate 2 protons. Hey, I hope we are all on the same page. Okay, cleos. Now, what then do we look at? We look at number 3. Remember, the number of hydrogen atoms in a substance tell you how many protons it can lose. So I have H3PO4. I then notice something. What do you notice? What do you notice according to the number of protons? It has 3 hydrogen atoms, meaning it can lose or donate how many? There we go. It can donate 3 protons. Right. Now, what do we call something that can actually donate 3 protons? Okay, so we say that's the case, and we are saying that it can donate H3PO4 can basically donate 3 protons, right? And what do we call that? We call that a triprotic acid. Call that a triprotic acid. Remember, mathematics, once again, tri means 3, right? Okay, so the ionization of phosphoric acid works just as similar as it did in sulfuric acid. So let's see how it happens. So I initially start with phosphoric acid, H3PO4, and then I ionize it, and then it gives me H2PO4 minus plus a proton. Remember, -1 proton at a time. We're not going to do it all at the same time. So what then do you notice? You then notice that I have 3 hydrogen atoms, so I'm expected to lose 3 protons, right? So what happens here? The first reaction, the first ionization, left me with H2PO4. Now I have 2 hydrogens. Why not 3? Because I lost 1. And why did I lost 1 proton? Now this -1 here tells me that I've lost 1 proton. Right? Hope you guys are getting the trend in this. Now notice something again. H2PO4 still has 2 hydrogens, meaning it can lose 2 more hydrogens. Therefore, we take it again and we have H2PO4 minus, right? And then what does that give me? It gives me H, PO4, 2 minus, plus, and H plus. You then notice something. What do you notice? You notice the 2 minus. What does it tell you? It tells you that I have lost my second proton. I have lost my second proton. So relative, or with reference to that guy over there, the phosphoric acid, reference to the phosphoric acid, I have only lost 2 protons thus far, which are this guy and this guy. These are the 2 protons that I have lost, right? And I say, okay, what then do? I then say H, P, O4, 2 minus. Remember, I had one H left, which I can still lose. What then do I have? I have PO4, 3 minus, plus a proton. Why? Now this tells me that I have a charge of 3 minus. Relative to the real guy here, I've lost so far 3 protons, right? I then say, okay, I've lost 3 protons. Where's the proton I've lost? Right there. So this one is my third proton. So how many protons have I lost thus far? I lost this guy right here, this guy right here, and this guy right here. So I've lost these 3 protons. Right. Are there any protons I can still lose from PO4 minus? No. So from PO4 3 minus, I have no more H pluses to donate. Therefore, this will then be the final part. Now, how many protons have I lost? How many protons have I lost? I've lost 1 H plus another H plus, right? Plus another H plus, which gives me 3 H pluses that I've lost. How did we know? We saw that it had 3 hydrogen atoms, meaning it can donate 3 protons. Hey, right. I think that's just about everything. So what have we looked at? We have looked at the Arrhenius theory definition of an acid and a base, right? We said that an acid is a substance that produces hydronium ions in water. A base is a substance that produces hydroxide ions in water. And then according to the Laurie-Bronsted theory, an acid is a proton donor, a base is a proton acceptor. We've looked at the fact that acids ionize, bases dissociate, right? We've looked at typical examples of how an acid basically works and how a base basically works. We talked about acid proticity and how the number of atoms of hydrogen in an acid basically tell me how many protons it can lose, right? Just very strict on the grade 11 content, just sticks to that part, right? It changes as your grades increase, right? And we've looked at acid proticity, we've looked at monoprotic acid, we've looked at diprotic acids, triprotic acids, and of course, if you have a certain acid that can donate more than 3 acids, then we obviously refer to that as not a quadruple. I'm pretty sure someone was thinking of a what would you actually call it? Quadruprotic. Ooh, okay, that's a fancy word. You could call it a quadruprotic acid, but no, this is not really, we don't talk about this. We talk about polyprotic acids. Polyprotic acids. We talk about polyprotic acids when it's something more than 3. Okay, but anyway, in the next video, I'll be talking about conjugate acid-base pairs. I'll be talking about ampholytes. I'll be talking about weak acids and strong acids and concentrated acids and dilute acids and a pH scale. It's going to be a blast of acids and bases. But anyway, please don't forget to like, comment, share, and subscribe. And thank you for watching the video. See you in the next one.